Hey guys, and welcome back. This is Jason with Alabama Science in Motion. I'm the physics specialist at Jacksonville State University. And so this video today, we're going to do a quick overview of the lab that we entitle Work in Kinetic Energy. So materials for this lab, we're going to need a 1.2 meter dynamics track. We're going to be using the Pasco smart card as well. And we've got a hook screwed into the force sensor on that card. For the first two runs, we're going to keep the card empty. And then for the second two runs of data, we're going to put a couple of 100-gram masses on top of the cart just to weight it down. I've got a piece of braided physics string. There we can see it. I've got this braided physics string connected to the hook, running through an end stop and going over a super pulley on the other end of the track. Make sure, as always, that the track is level on this lab. It will greatly change your results if it's not. Also, make sure that this super pulley is adjusted level and tight as well. So you want to try and keep the string level. The instructions, as currently written, have 30 grams of mass on the hanger. I find that that's almost a little too much for an empty smart cart. So I've just got a 20-gram mass on this 5-gram hanger. So all we're going to do in the lab is it's really simple. For the first two runs, we're going to leave the cart empty. Students will mash record in their software. Now, there's still a Bluetooth lag, so they need to wait a moment till they tell the data is active. But what's neat is it won't actually take any data until the students release the cart. And what's also neat is the software, we've got the file pre-programmed to cut off after about 60 centimeters. So the students will press record, wait till they see it's active, let go of the cart, allow it to roll down the track, and it'll cut itself off after it's rolled about 60 centimeters. The reason why we do this is because of the lag time. Students can't actually reaction time fast enough to turn off the software. For runs, so for the first two runs, they'll do it with the cart empty. For the second two runs, they'll repeat, but they'll add 200 grams to the top of the cart, and then it'll be the same thing again. They'll take, release the cart, and if you're wondering, wow, it's going very slow this time, it's because of something the students miss as well. My strings jumped off the pulley. So anyway, things to keep in mind on the pulleys. Join y'all in a second as we kind of take a look at the rest of this lab.
So here we go, and let's kind of move further through this video, and let's go straight to the data table that we've actually got here. So the essential question in this lab will probably be updated pretty soon, but what we're really looking at in this lab, we're trying to find what relationship exists between the work done on an object and that object's change in kinetic energy. Now, we know that work is equal to delta KE. We know it's equal to a change in kinetic energy, and I don't like writing work like that. We need to write work net when we write that out, because that's a more realistic statement, because anything that can make a force can actually do work. But what we're looking at in this lab, if you remember, we've got a cart, and let's see if we can go back and look at a little diagram from this lab. We've got a diagram of a cart, and that cart is actually being pulled with a force, and that force is because of the force of gravity. Now, one of the things I like talking about here in terms of doing this lab is I like having students look at these two graphs, a force position graph and a velocity position graph. So I'm going to write force times distance, a force distance graph, and a velocity distance graph. Now, what's interesting is this. These are not pre-lab questions, but I actually, when I'm running the lab, I actually ask these two graphs as a pre-lab question, because for some reason, students tend to all go through and draw a force distance graph where they show this line like this. And so I always like going back and taking a moment and going back to the diagram in the lab and asking, well, what is it that makes the cart move down the track? Well, it's that force, and it's due to gravity. So then usually most of them that mess up will then realize, well, the gravity's not changing. The mass on the hanger isn't changing. If you remember, I put 20 grams on my hanger. It keeps the cart from going too fast. And so usually the students then will reconsider at that point, and then we can talk about, well, what should a constant force look like on the graph? and usually then they'll come back and draw that across there. The velocity distance graph, they tend to mess it up as well, because they don't draw a lot of velocity distance graphs. But in our falling marble lab, they actually did graph this relationship in the falling marble, and it come up like this. If you remember, this relationship is actually a y square equals x type of relationship. So again, we addressed that in earlier labs. Ask it as a pre-lab. I don't think there's anything wrong with doing that. A lot of people, though, they're kind of like, hey, Jason, I think it's just as easy for me just to write on the board and tell them that work net is equal to changing kinetic energy. Well, okay, but I think you're missing out on something really nice about this lab. Not only are we using a lab to actually find this relationship as opposed to just giving it straight out of a textbook, but we're missing a good opportunity here. See, the cart, look at the data table. The instructions are very simple. First, they'll write the mass of the cart. Mine's 0.248. So there's the mass of my cart, 2 grams short of its 50 grams. But here's what's also interesting. The data we're going to get, you see, we're always asking students to find slope of a graph, find the slope. So what is the slope of a force distance graph? Well, I'll go ahead and tell you, it's nothing. There is nothing that is slope of force over distance. So this gives us a great opportunity, and I love this for AP students. One of the things we always do before an AP test is go through and I'll draw random graphs. Here, give me a blank page. I'll start drawing random graphs on the board, like velocity time, and asking my AP students, okay, does slope mean anything from this graph? Well, the slope of velocity over time, wait a minute, that's acceleration. And then we always say, okay, well, likewise, does the area of this graph, does velocity times time mean anything? Oh, wait, that's position, x. And so it's a good game to play, particularly with the AP students. So in the case of this lab, slope of a force distance graph didn't mean nothing, so ask your students. What about force times distance? Well, they should have already, prior to this lab, had what work is defined, a force times a distance. So that will tell them that the area of this force distance graph, the area under that curve, if you wanted to write it this way, we could write it like this. The area underneath that curve, that is actually equal to the work done on this cart. So the computer is going to tell us this area under the curve, and that's going to give us the work. We're going to get an initial velocity, which should basically be 0. We're going to release it from rest. And then what we're going to do is this. From the velocity time graph, we should be able to get this velocity max right when the computer shuts itself off. So now let's take a look at Capstone, and let's actually go in and do that computer portion of the lab. So I'm going to turn on my smart cart, and we should see it pop up now that I've clicked hardware setup. I'll connect to number 243. It's the only one I have on right now. And I've got it connected. My battery's good, so I'm going to close it. I've got my force and velocity position graphs. And what's kind of neat on the setup of this lab, I've done a couple of things to try and make it a little bit easier on the students. Now, if you remember, there's always a Bluetooth lag, so I'm not going to let go of the cart till I see data. So I'm going to pull my cart back. It's empty at this time. I'm going to mash record. And I can tell the card is now active, but notice something, 4 or 5 seconds, nothing's happened. I haven't released it yet. I've got it set so that it doesn't actually record data till I let it go. And you know what? I've actually forgot a major step in this lab. So I'm going to click stop without even doing anything. Because something I forgot to do was this, and it's very implicitly written in the instructions. Look down here to where it says Smart Cart Force Sensor. I've got the sample rate at 50 Hertz, and out beside it, I'll hold my mouse over it, 0 sensor now. Now, this is very important in order to make this lab come out with decent data. I've got to actually unhook the string. So if we go back to the setup, I've got to disconnect this string. There's usually a little stray potential in the sensor. So unhook the string. It's important to have the students do this before every single run. Unhook their string, I'll return back to my main page, and now I'm going to hit the 0 button. So I'm going to hit the 0, and now I'm going to hook the sensor back up. So I'm going to hook the string back to the sensor. Now let's actually do this. So press record and wait for it, and I see that everything is alive. And now I'm going to release the cart, and what's cool is I've pre-programmed this to stop after it rolls 50 centimeters. So I'll let go, and if you look, I did not have to press stop. The reason why I do that is because student reaction time just isn't good enough to be able to do this. So I've got all my data on this. Now, if you were really wanting to go harder with the students, what you could do here, I'm going to do something. I'm going to add a blank page. If you wanted to with your students, don't use this pre-made file. Go over to where you see the graph. I'm over on the right side of the displays. I'm dragging graph onto my screen. I'm going to go up to where it says add new plot area, add new plot area. And now what you could actually do is just do this from scratch. And so select force for the first one, select velocity for my second graph, and I could also go down to the bottom and change any settings I wanted to. I just like showing you this so that you're not always dependent on these pre-made files. I think the students get a good bit of ownership by actually taking the data themselves. I'm going to zoom out because what's cool about this is now I can actually go up here, and the area button is display area under the highlighted area. I'm going to click on that graph, and there. That's how I actually get the area. I can actually click that. You could go down to as well to this bottom graph, which doesn't look very curved right now. Let's see if I can actually blow that up. Oh, that's because I've messed up. This is time. So let's make this velocity. There we go. That's much better. Now we've got these force position graphs. So now I've been able to calculate a work up here because I've got an area of this graph. Down here, I could actually go in. I actually did this. If I want you to know how the setup file was made, I did the statistics button, and I let it just show the maximum on this graph. Let's see if I can get it to actually display it this time. So give me my statistics, please. And so there is my maximum. I'm allowing it to show off the graph. You could also have students use the multi-coordinate tool, and they could actually scroll across their data, and they could find that last velocity before it hit. But anyway, I'm going to go back to the pre-made file. And so the pre-made file, it comes out very nice and pretty. There's my area that I can write down on my data table. So my first area was 0.088 Newton meters. And then it says my velocity initial. Well, I know it was 0 because I let go of the cart. It didn't start recording data till it had actually moved. And then my maximum velocity, let's see if we can go back, look at my maximum. So flipping back over, my average velocity is 429. My maximum velocity was 0.825. I could also verify that again if I wanted to use like a coordinate tool or something. I could go find that last velocity out there, but the statistics mode works pretty well for that as well. So we said 0.825. So we've got 0.825. And now we'll go down to number 1, and it asks us to find our change in kinetic energy. Well, I'm going to call our kinetic energy initial. I'm just going to call it 0. And simply because it kind of does make the calculation a little easier. If you really wanted to, you could actually have your students calculate based on this 0.028 minimum velocity, and you could use that. I would suggest use it with your class. If your class is pretty good, then go ahead and take this 0.28. If not, you might just let them stay with 0. Let's see. Now we need to calculate our final velocity. So our kinetic energy final is equal to, well, let's write out 1/2 mv squared. Or in this case, 1/2 mass times velocity final square. And the mass of our cart was 0.248 kilograms. And our velocity was 0.825. And boy, is my screen giving me some problems. So I'm just going to write square. Now let's see if we can type that into a calculator and bring up my calculator, and I've actually already typed it in there. So it comes out to 0.084 joules. Now that's interesting. 0.084 joules is what our answer comes out to. Now, the next part we're asked to do, and the calculations are the same for each and every trial. So all we need to do for the rest of it is we're just going to compare those two values, 0.88 and 0.84. Now, I love this because this will be great calculations. The top is the difference, so our difference is 0.04. The bottom is simply the average of the two values, which would be 0.086, and we'll times that by 100. And let's see what we get. Difference divided by the average times 100. So 0.004 divided by 0.086 times 100 would be 4.7%, which is actually pretty great. 4.7% for a percent difference in this lab. And I'll be honest, if you go through and the two runs where you actually add mass to the cart, those are actually even better. Usually your data should get better. So I don't think we can complain about 4.7%. There's a little part of me almost wants to go back and see what we would have if we actually took that 0.29 meter per second instant velocity or initial velocity in there. Let's give that a shot real quick. I should have it in here somewhere. So let's rewind the calculation for a second. Let's just see what would happen if we actually included that 0.29 initial velocity. Woo, that gives us an initial kinetic energy of 1 times 10 to the negative 4. Let's see, and now we'll subtract that from, take the difference from 0.084, and that gives us still a 0.084 change in kinetic energy. So I think if nothing else, I've proved by doing that just calling that initial velocity 0, it makes the only difference is down to the 10,000ths of a joule. So I think we're pretty safe in just calling that 0. And so we can also finish this up with 4.7. There is another portion to the lab that actually does some more work in kinetic energy calculations. I'll make a separate video on that, but this is the primary part of the lab. Anyway, so thanks for watching. Hope you kind of got an understanding of everything. Bye.